we are finishing up our last section. We'll review tomorrow, test on...
Oh, she didn't even read it.
I'll do it later. Test on Thursday. Just realized it's recording right now too. So, this is our last topic of Chapter 4. Chapter 5 will involve a lot of word problems. We're going to take our basic knowledge and apply it to a lot of application problems. Word apply. And then we'll actually start talking about integration pretty soon after that. So we're almost getting to the second half of calculus. It's exciting. So first, I wanted to review some of our logarithm rules. Things you should have seen in pre-calc, but may have forgotten at this point. Please don't add.
Don't worry, Josh. When this is recording, I probably won't die.
So natural log of a times b. How can I rewrite that using my logarithmic rules? The multiply changed to something.
Couldn't you do like ln of a plus ln of b?
Ln of a plus ln of b. Now it's very similar to the same exponential property. If I had x to the a times x to the b, you would know immediately, hey, I add a plus b. They're opposites, so it's a little bit different. Here we're splitting them apart instead of putting them together. But it's basically the same rule, just for the inverse function. So what if I have a divided by b?
So minus.
Minus. Divide means minus. Ugh. Wrote an extra minus sign that I did not mean. These also work for just basic logarithm. I can say log base a. Just more often we work with natural log in calculus. It's the most common one we work with. If I have natural log of a to the b, what do we do when we have an exponent inside?
You bring it down.
Bring it in front and multiply. B times ln a. What about natural log of 1? This is a value you should have memorized. Natural log of 1. Okay, let's think of it this way. We're trying to figure out this value. We know this is log base e of 1 equals some number. Do you guys remember how to rewrite this as an exponential?
E to the question mark equals 1. So
E to the question mark equals 1. So what would question mark have to be to make a 1? 0. So natural log of 1 is 0. And it is good to know how to rewrite things from exponential to logarithmic format. So if I had log base a of x equal to y, then we would get a to the y equals x. Those are the same thing written 2 different ways. I know it's weird to consider those are the same, but those are the same thing. Just written as exponential or written as logarithmic. And then the last one you might need to know is if you ever do have to do a change of base, this one might not ever need, but just in case. If I ever need to do change of base, because our calculator usually only does base 10, obviously the TI Inspires will do other bases. But in case for some reason we need to simplify or rewrite this in a different base, log my new base, I'm going to say base A of x divided by log base A of b. Again, those are the same thing written two different ways.
Where'd the
You can make it anything you want,
We could see.
as long as they're both C. I could, so you don't have to write this down, but just to show you, if I had log base 7 of 10, okay. Now most of the time we can't, oh that's one more thing, I'm glad I wrote this one up here. Most of the time we couldn't plug this into a calculator because our calculators would only be base 10. It's more of a thing of a past, but just again so you can see, well if I want to plug it into a calculator, I could say log base 10 of 10 over log base 10 of 7. And those are actually the same thing, and usually the sole purpose of change of base is to be able to plug it into a calculator. That's why I say we might not use this much, but it's still good to have in our back pocket. Or what if I wanted to use natural log instead, natural log of 10 and natural log of 7. All three things, if I plug them into a calculator, would be the same decimal. I could say log base 1 million of 10 divided by log base 1 million of 7. Oh, always. What if I'm running out of room, I should have left more room for my natural log rules. What if I do natural log of e to the x? What happens when you natural log e? It gives you 1, but where we have this exponent out front, we have x times natural log of e, which is x times 1, which is x. Basically, since natural log and e are opposites, I could have just canceled those out and said this equals x. And I could do the same thing backwards. If I did e to the natural log, the e and the natural log would cancel each other out. The only thing we do have to watch for, if we have natural log of natural log, I can't do anything about that. Sorry, again, I ran out of room, so it starts getting squished. But natural log of natural log, nothing I can do about that. Just like if we had sine of sine, we'd be stuck. So, review of our logarithmic rules. Now we're going to be attacking some harder tangent line questions. That's what I meant by applications. So far, most of our tangent line questions have been fairly straightforward. We've done a few that are kind of a more critical thinking process. But these two tangent line questions are going to test our critical thinking skills of what do we know, what are we trying to find, how can I get there? And then after we do the tangent line questions, we'll talk about logarithmic differentiation. So this example, at what point on the graph y equals 2e to the x minus 1 is the tangent line perpendicular to the line negative 3x plus 2? So as with any critical thinking question, this goes the same for the ACT, for those of you who are taking the ACT soon, we need to identify what is it asking for? What's our goal? Because if we don't know what we're trying to reach, we won't know if we're there or not. So ultimately, what is our goal with this one? What does it ask us to find? Point on the graph. We want to find a point, x comma y, that fits this equation, y equals 2e to the x minus 1. So our goal is to find that point, x comma y. So now we need to know what information do we have. Well, we have the equation of the function, y equals 2e to the x minus 1. That's pretty straightforward because I wrote it down for us. What other information do we have?
We know the slope of the, what we define.
Okay, we know slope. And how do we know slope?
It's the inverse of the line.
Okay. It's the opposite reciprocal. We always want to say inverse, but it's actually opposite reciprocal of the slope of the line. So what's the slope of my line here? -3. So in our no column, things we know slope is positive 1/3. We flip it, change the sign. So that's all the information I can glean so far from the question. I know an equation for a function. I know a slope. So now we have to relate the stuff we know together. So we know a function, we know a slope. How can we relate these two things together? What could we do to this equation so that it would actually relate to our slope? Why would we choose derivative?
Because the derivative is the slope.
Derivative is slope. So if I found y prime should equal 1/3 because derivative is slope. So let's find y prime. What is the derivative of 2e to the x? First, what's the derivative of e to the x? E to the x. If there's a coefficient in front, it doesn't change anything. We still just take the derivative of e to the x, which is e to the x. So the derivative of 2e to the x is 2e to the x. What about derivative of 1? 0. Don't write it in. So we get 2e to the x equals 1/3. I need to solve for x now. Once I have an equation with only one variable, I can solve for that variable. So what should I do to solve for x? We can only do that if we only have e to the x on that left side. So we've got to do something with the 2 first, and then we will natural log. Divide by 2. Write it differently on the right because we're working with fractions. For me, I really need old school fraction notation. So when I divide by 2, that's the same as timesing by 1/2. So you get e to the x equals 1/6. And then, as Emma said, we could natural log both sides to get rid of e. I can do whatever I want to both sides as long as I do the same thing to both sides. What I want to do is ln both sides. Just give us a little more room. So that means my natural log and my e cancel. We have x equals ln of 1 divided by 6. Now at this point we do need to do some simplification using our logarithmic rules. What could I do to simplify this?
It would be the natural log of 1 minus the natural log of 6.
Natural log of 1 minus natural log of 6. And there's something else I should recognize when I do that.
Natural log of 1 is 0.
Natural log of 1 is 0. So now we know x equals negative ln of 6. Now that's a weird x to find, but they like leaving things in terms of natural log, or saying e to the 1/3 is your value. So we've got to think of values as more than just the counting numbers, 1, 2, 3, or fractions. Values can be natural logs now, they can be e to the 5. That's an actual value. If we calculated it out, it'd be some weird decimal, but it's still just a number. So we have x equals negative natural log of 6. So we're close to achieving our goal. What are we missing? Need to plug it in and find y. So we take y equals 2e to the negative ln 6 minus 1. Now I can't cancel e to the negative ln. That negative makes it different. But what can I do with a negative exponent? If that was negative 6 without the ln, what would we do? Move it to the bottom. So we have 2 over e ln 6 minus 1. And now that it's positive, we can do some cancel. Now I can cancel my e and my ln. We would have 2 over 6, which is the same as 1/3. Minus 1 is negative 2/3. So again, like I said, probably one of the weirdest parts of these processes, I think, is thinking in terms of the fact that ln 6 is actually a value. It's a number.
So why does e to the ln cancel?
E to the ln cancels because, oh, okay, hold on. I'm going to need some blank space to prove that for you. Let me finish just writing the answer. So our final answer is negative ln 6 comma negative 2/3 e to the ln 6. So I'm going to go just to a blank page so I can prove this. Ln 6. Okay, let's say this equals x. We can rewrite this in logarithmic form. So in logarithmic form, we would have log. What would be our base? The base is the same as what would be the base of that exponential function? When we think of exponential functions, what is the base of an exponential function? E, if we have like 2 to the x, 2 is the base. If I have 5 to the x, 5 is the base. It's the number, not coefficient. So base e of x equals this exponent, ln 6. But what do we know log base e really is? Natural log. So if natural log x equals natural log 6, what does x have to equal? 6. So therefore, e and natural log just cancel because we know x equals 6. So if these go away, 6 equals x. Proof. Sometimes when I'm asked proof questions, I can't always do it, so I'm always proud when I can. Okay, so now I want you guys to try this one. This one is a little bit more different. Again, we have to focus on some of our critical thinking skills. Our question is, what do we know? What are we going to? And usually the hardest part is then, how do we get there from what we know? I got most of you guys to a point. Most of you guys took the derivative. You could do chain rule, or you could rewrite as ln x minus ln 3. So most of you guys got y prime is 1 over x. Actually, I think all of you guys got y prime is 1 over x. I walked you through the slope of, or the equation of a tangent line. Y minus 0 equals m times x minus 0. So y is mx. And then we said, what do we know about the derivative? Derivative is slope. So instead of m, I could write 1 over x, which is 1. So now I know a y value. And what I specifically want to talk about is how we find our x value. There's 2 different options. We still have to use the equation. We could write it as 1 equals ln x minus ln 3. Or we could go back to the original, 1 equals ln x divided by 3. In this case, I think the right one is a little bit simpler for finding, so this is just about pre-calc, it's not about calculus. I think this one is easier to solve for than that one, but both work. So if I want to get rid of ln, what do we do now to get rid of ln?
Times by
Not times by e, raise everything to e. Okay? It's e raised to the 1, e raised to the ln of x over 3. Often we just write it in kind of below what's already there. We e it. Just like I can natural log both sides, I can e both sides. Well, we know e to the first is e. And what did we just learn about e to the natural log? Cancels out. And now I just solve for x. How do I get x alone? Times by 3. So x is 3e, which would make our final answer, our slope, 1 over 3e. We'd have to plug it in to get our final answer. Now I can still solve this other one. I feel like it's a little bit more complicated, but it may be the easier way for you. So we add ln 3. We have 1 plus ln 3 equals ln x. And then to get rid of ln, I still e it. That step's not going to change. I put e on both sides. So we would get e to the 1 plus ln 3 equals x. And now here again is where we need to be more flexible with some of our pre-calc knowledge. We're really good at taking x to the a times x to the b and writing it as x to the a plus b. We're really bad at taking x to the a plus b and writing it as x to the a times x to the b. You don't practice it as much in that direction. But just like any formula, I can use it from left to right or right to left. So I can change this plus sign and say e to the first times e to the ln 3. And then, what do we know about e to the ln? Cancels. So again, we get 3e. And this is a tactic we need to become more comfortable with. Taking a plus sign in your exponents and rewriting this as multiply. When we get to separation of variables, which is way down the line, this is a very important skill, being able to do that property backwards. Okay, so let's talk about logarithmic differentiation. Does everyone have this down before I go to the next page then? Enough. So when we are doing logarithmic differentiation, it applies to two certain situations, two setups. When we have a variable raised to, should have given myself more room, a variable. Or if we have a super duper complicated derivative, super complicated derivative. Or in other words, a complex derivative, but taking the complex derivatives we did and making them cry like babies. Nothing.
Oh,
Thanks for the pity laugh. Maybe you'll get
Did
some
you
pity
start the
grade
thingy
points.
back?
I did. Thank you. Okay, so here's the case of a variable to a variable. So when we do logarithmic differentiation, its purpose is because I cannot use power rule on this. Cannot. Don't use power rule. Can't use. Why can I not use power rule?
12 is not.
because it's x to the x. Power rule only applies to x to a number, not x to the x. And same thing, I can't use my exponential derivative formula because that's a number to a variable. If we have a variable to a variable, can't use power rule. So we need to do something in order to get this exponent not to be an exponent anymore. I can't have an exponent to an exponent. So we go back to our logarithmic rules. What did logarithms do to an exponent?
They bring it down in front.
They bring it down in front. So if I natural log both sides, usually we natural log both sides to get rid of e. In this case, my sole purpose in natural logging both sides, get that exponent down and not be an exponent anymore. So when I do that, I can't just drop natural log of y. It's still there. We have natural log of y, and then I'm bringing the 2x minus 1 in front times natural log of x. So at this point, I can actually take the derivative because we know how to take derivatives implicitly. So what would the derivative of natural log y be? 1 divided by y times y prime. Anytime we take the derivative of a y with respect to x, we have to multiply by that because really we're doing a chain rule. Derivative of the inside is y prime. How would I take the derivative of the right side? Product rule. So we have u is 2x minus 1, v is ln x. No super complicated derivatives here. Derivative of 2x minus 1 is 2. Derivative of ln x you will need to have memorized for the test. You may not have it memorized yet, but you can look them up for the homework. Derivative of ln x is 1 over x. So once we've taken the derivative of both pieces, we apply product rule. Low d high plus high d low. So ln x times 2 plus 2x minus 1 times 1 over x. I will not make you simplify everything, but we do need to get y prime alone. Just like with any implicit differentiation problem, we want our answer to say y prime equals blah. So what would y prime equal?
That whole thing divided by 1 over y.
And what's the whole thing divided by 1 over y? What's another way to think of dividing by 1 over y? Times by y. So we have this whole thing, ln x times 2 plus 2x minus 1 times 1 over x. We could do a little simplification there if you felt like it. Times y. But just like when we were taking the second derivative implicitly, if we can get everything in terms of x, we want to. What could I replace y with? X to the 2x minus 1. We originally said y equals x to the 2x minus 1. So we have, I'm going to simplify this just a tiny bit, put the 2 in front of ln, put the 2x minus 1 over the x, times x to the 2x minus 1. Don't simplify any further. So the last thing we want to talk about is how are we going to use logarithmic differentiation to help us with super complex derivatives, complex derivatives on steroids. So before I move to the next page, though, I want to make sure everyone has this written down. should you do if you fight a group of clowns? Wait for it. Go for the juggler.
No.
Oh, sorry, I thought we were done. I was just trying to entertain people until everyone was done.
Okay, good.
Okay.
That's terrible.
The more I
Okay.
think about it, the funnier it gets.
Hmm?
The more I think about it, the funnier it gets.
It's one of my favorites. So if I were to do this derivative without doing logarithmic differentiation, what rules would I have to use?
Quotient power.
Quotient power, chain. Oh, it's not quotient power, quotient product.
Or
Power.
product.
Chain. Chain again. We'd be using a lot. This would not just be pro quo or quote chain or chain. It would be quo, pro, chain, pro, chain. I think that's it. No power mixed in there, but we hardly ever say power since it's a little more intuitive. But if I use the same tactic I used on the previous problem, I can make this still a very long problem, a long derivative, but a lot easier to take the derivative of. So what tactic did we use? What did we start with? We take the natural log of both sides. And I do that because now I can split this all apart into plus and minus signs. We can take the derivatives of plus and minuses a lot easier because we can take them separately. We don't have to use all the rules at once. So I have ln, not taking the derivative yet. I would have 2x minus 1, so ln of 2x minus 1. Am I going to plus or minus the 5x? Plus. Ln of, and I'm going to put this in parentheses and write it to the 1/2. And then minus these bottom ones. So minus ln of x cubed minus ln of 3x squared minus 1 to the 1/2. Everything on top gets a plus sign, everything on bottom gets a minus sign. So yes, it's a very long derivative, but especially once we get rid of those exponents, a lot quicker to take the derivative of instead of doing quo pro chain, whatever else is thrown in.
So we completely space how to do this, and we have to do it really long.
Yes,
But
this is
it's
only
limited range of
this is
zero.
only an advantage if you remember to use it. Right now, since we're in this specific section, hopefully you will remember to use it. But when we get to the AP test, we have to remind ourselves of those little details again, because they make the difference between 3 to 5.
G is still a 4.
So what do I do with these powers that were up here?
Oh, you can put them down in the front.
I can put them down in front. Then they're coefficients. This makes it even better for us, because their derivative of a coefficient stays. So we have ln equals ln 2x minus 1 plus 1/2 ln of 5x plus 7 minus 3 ln x minus 1/2. And we really could have done that within the same step if we wanted. But I just didn't want to do too many of these properties at once since we're still refreshing on them. Okay, so now we can take the derivative, and we do need chain rule, but we only have to do chain rule once on each piece. We don't have to have a whole bunch of rules together. So same thing over here, derivative of ln y is 1 over y times y prime. And all the rest are basically the same. 1 over what's on the inside, times the derivative of the inside. So 1 over 2x minus 1 times what? 2. And I could write out the chain rule, but we get in a nice pattern with these where they all are very similar. So plus 1/2 times 1 over 5x plus 7 times 5. Coefficient is still there. We put 1 over, because the derivative of natural log is 1 over the inside, times the derivative of the inside. Minus 3 times 1 over x. I could do times 1 if I wanted to do chain rule on that as well, but why bother? Minus 1/2 times 1 over 3x squared minus 1 times 6x. So yes, still a very long derivative to write out. But taking that derivative is a lot simpler than doing all those rules together. And then what was our final step for a problem like this? Multiply everything by y. So again, if you kind of want to combine the steps, especially since there's so much writing, on the homework, if you want to kind of combine and just write it out, y prime equals blah times y, that's fine. So we have 2 over 2x minus 1 plus 5 over 2 times 5x plus 7 minus 3 over x minus 6 and 2 cancel. 3x over 3x squared minus 1. That's why I said on the homework if you want to combine, so you don't have to write this line and this line.
Yeah.
Times the original, which I don't even remember anymore. X cubed was on bottom. Square root of
2x minus 1 times the square root of x plus 7,
was it x or 5x?
5x, divided by x cubed times the square root.
Yeah, square root minus 1. Okay. And that is our final answer. If we did use all those rules, quotient, product, chain, our answer would look a lot different. It would be the same. We would just have to take the time to simplify the two to be the same, which we don't want to do. So it is a longer process. Not necessarily a super difficult process, unless you struggle with your pre-calc logarithmic rules, which we are kind of refreshing. So does everyone have this down before I show you the homework? We will not have time to work on our assignment today.
Nope.
Quiz days, we don't usually have enough time to also, oh, I should not turn this off yet, so the homework is shown, so Melinda can see the homework assignment.
Hi, Melinda. Wait, is the -1 inside?
Yes, it is. Sorry, I was just sloppy because it was a lot to write.
Okay.
Okay, now are we ready for the homework?
Nope.
Josh is still ready.
I got it on my paper. You
Okay.
can go on.
So page 183, 29 through 31, those will be tangent line problems. 33, I forgot what that problem was, but 43 through 46 will be the logarithmic differentiation. So just 4 problems of the logarithmic differentiation.
Oh, George. There goes the whole place.
Oh, 33 was just kind of a make you think, don't get stuck in one pattern problem. So I don't want to give it away. So 33 is actually fairly simple if you see kind of the trick behind it.
Ben, don't take the entire thing.